Okay, so welcome to the last unit in the topic of bonding, metallic bonding. So we've looked at ionic bonding, where electrons are taken and given by atoms through forming of ions. We looked at covalent bonding, where atoms share electrons, and now we're going to look at metallic bonding. And so these are the three learning objectives for the final topic. Number one, know how to represent a metallic lattice in a 2D diagram. 2, understand that a metal can be described in terms of electrostatic attractions. And 3, explain the electrical conductivity and malleability of a metal in terms of its structure and its bonding. So we'll look into those terms as well and what they actually define.
Metals are used in many everyday objects. This morning, when I woke up, I decided to have a soft-boiled egg and a cup of coffee. The pot I used is made of metal. The kettle is made of plastic, but the coiled heating element inside it is made of metal. Metals are good conductors of heat. This is the reason why metals are used to make these everyday objects. You would never see a pot made of wood or a heating element made of plastic. Metals are also good conductors of electricity. The wire connecting your kettle to the electrical socket is actually made of many copper wires, insulated with a layer of rubber. Think about the shapes of the everyday objects we described. The pot, the heating element inside the kettle, and the copper wires. Notice that they are very different. Metals are malleable. This means that they can be molded into different shapes. Metals are very ductile. This means that they can be stretched into wires. To fully understand these properties of metals, we must understand metallic bonding. When we talk about metallic bonding, we are actually describing the electrostatic attraction between the metal ions arranged in a lattice structure and the free-floating electrons around them. Since these electrons are free to move around, the term sea of electrons is also used. What is a lattice structure, and where have you heard this term before? Let's pause the lesson to think about this and resume when you are done. The term lattice structure means that there is a regular repeating pattern. We have heard this term before when discussing ionic lattices. It is used to describe the alternating positions of the metal and nonmetal ions. In metallic structures, however, there are only metal ions. These metal ions are arranged side by side in a regular repeating pattern. The free-floating electrons act like a glue and hold the structure in place. This is a very strong attraction and explains why metals have high melting and boiling points. A lot of heat energy is needed to overcome this attraction. This is also why metals are very good conductors of heat. Free-floating electrons are the reason why metals can conduct electricity. Metals are malleable and ductile because no matter what shape the metal takes, the free-floating electrons will conform to that shape. The strong electrostatic attraction will remain, and therefore the structure stays intact. Let's think about it. Cars and bicycles, trains, planes, buildings, cutlery, spectacles, furniture, and endless items can be made from metals. To recap, the electrostatic attraction between metal ions arranged in a lattice structure and free-floating electrons is known as metallic bonding. This explains many properties of metals. They are good conductors of heat and electricity, have high melting and boiling points, and are malleable and ductile.
structure of metals. So sodium is a metal, and when sodium atoms bond together, they form a solid metal with the outer electrons of each sodium atom becoming free to move throughout the whole structure. So metals can be essentially described as a giant structure of positive ions surrounded by a sea of delocalized electrons. The electrons are no longer attached to particular atoms or pairs of atoms. Instead, you can think of them as flowing around the whole metal, like this particular example here. Okay, so these here are your free electrons, okay, these free valence electrons, and they are free. So when a metal atom loses its outer electron to become a metal ion, that is what is left behind. A metallic structure consists of a lattice, or a regular arrangement of positive ions in a sea of delocalized electrons, which is what we observe. Okay, basically these electrons are all smeared or delocalized over all the positive metal ions. Because of this, the electrons are free to roam across the metal, so they are shared by all the metal ions. So metallic bonding is the electrostatic forces of attraction between each positive ion and the delocalized electrons. And this holds the structure together. And these are the properties of metals and non-metals. So metals are shiny compared to non-metals. They are solid usually at room temperature compared to non-metals. They have high density compared to non-metals. They're stronger than non-metals. Remembering, of course, non-metals tend to have covalent bonding. They are malleable, which means they bend without breaking. They are good conductors of both electricity and heat, which we'll look at in more detail in the next few slides, whereas non-metals are poor, essentially because in non-metals with covalent bonding, the electrons have been shared, they can't move around, and they tend to be three metals are magnetic, iron, cobalt, and nickel, and no non-metals are magnetic. And they are sonorous metals when you hit them, whereas non-metals are dull sounding. Okay, so metals conduct electricity because they have these delocalized electrons, okay, and they are free to move throughout the structure. Imagine what happens if a piece of metal is attracted to an electrical power source, which is what we see here. Because they're free to move, if we look at this diagram, we have a negative terminal and a positive terminal. Electrons are negative, okay, so electrons are attracted to the positive terminal, okay, and they flow this way along a metallic wire. More electrons flow along the wire from the negative terminal, this guy here, okay, of the power source to replace those moving away from the moving away in the metal, which we're seeing in the diagram. Okay, so that is electrical conductivity, and it's the same also with heat conductivity because they're so close together. The heat can easily transfer from atom to atom. Okay, so this diagram here illustrates the reasoning why electrons can flow, why there is electricity. Okay, because remember, you need to have electrons being able to move in order for a charge or electrical current to flow in a circuit to have electricity. So another quality of metals is, of course, malleability. Okay, so when we say a metal is malleable, it means it's the substance's ability to change shape or deform under pressure when a force is applied. Okay, if it is malleable, a material may be flattened into thin sheets like gold leaf by hammering or by rolling. Okay, so this does not affect the bonding in the structure. If you look at this following diagram coming up, because the metallic bonds are strong enough to keep the atoms in place once the force has been removed. Okay, so if we apply a force to a piece of metal, the layers of positive ions basically slide over each other. Okay, Okay, they're beginning to roll over each other in this second step. Once the force is removed due to the positive and negative electric attraction between the delocalized outer electrons of the metals and the metallic ions, the layers fall back into their original positions. Okay, because the positive ions are still attracted to the delocalized electrons. Okay, so metallic bonds are characterized by a sea of these delocalized electrons that easily move from atom to another, and that allows the metal atoms to slide past each other if this force is applied. Metals can also be described as something called ductile, okay, and this means that they can be drawn into wires for similar reasons as to why they are malleable. And that is pretty much all you need to know for metallic bonding for IGCSE.